Welcome back here from our break. Let me just kind of scan around here. Okay, I think I got everything. And so let's kind of shift gears a little bit. And I'll start by saying that this then is some new material. And we'll spend, it looks like, a little over an hour kind of talking about this. But I'll also emphasize, as I'm sure you're well aware of, this is not on the upcoming exam, right? The upcoming exam is up to Chapter 11. And so the stuff we just wrapped up on Chapter 12, as well as these next couple of chapters, are not on the exam. But I do want to say then, as we shift gears, we are now leaving, I would say, mechanics completely. In other words, the first 10 chapters were the mechanics of solids. Then I said, hey, we were doing something different, and we did fluids for the last 2 chapters. I would still say it's the physics of fluid mechanics, so we're kind of still in that realm of mechanics. But now you'll see we're going to get into what we call thermodynamics. What is heat, and what is temperature, and what are the 3 laws of thermodynamics. And so this is my way of saying then, in your mind, you should group these 3 together. And sort of like we did Newton's 3 laws of motion in chapters 4, 5, and 6, and they were kind of all grouped together. That's what I want to say about chapters 13, 14, and 15. And so let's begin here with 13, and I'll begin by saying we are going to do chapter 13.1 through 13.4, meaning we will not do 13.5 and 13.6. And so they're interesting, they're neat, but I got more of the impression that it was just too much, and it wasn't really connected so much for the life science person. So I go, okay, let me use this as an opportunity to say, all right, let's not cover the whole chapter. Let's just do sections 1 through 4. All right, so where does this begin? And this chapter begins with a very interesting and important behavior called thermal expansion. And we call it thermal expansion because, as the name implies, if you warm something up, it gets bigger. Now, I want to be careful with that phrase, but let me just begin by actually demonstrating thermal expansion. I'll start here. You've watched me do this a few times, and you're going to see it a lot more, that if I were to turn this on and say, this is the visual picture I want you to have of what's happening to the molecules. And so for a gas, they're just kind of bouncing around and they're separated. But even if it's not a gas, it's more this pattern, which you remember me pointing this out for the liquid. This is these atoms that they're kind of connected together, but they can flow past each other. But my model doesn't really show it, but these are actually shaking in here. They're just shaking and bouncing off each other. So they're slightly connected to each other. And so they are different between this, which is the liquid model, and this, which is the gas model. But do you see how they're both shaking? Oh, likewise, this is my model of a solid. See, a solid, they're actually hooked together. But again, this doesn't do a complete picture. You got to imagine these atoms hooked together, but each of them individually are vibrating. They are shaking. Now, they're hooked together so they can't move away from their nearest neighbor. And so this is a solid, whereas a liquid, they don't have to stay next to their neighbor. That red one, which was by the blue one, is now by the pink one. And so as you shake it, it moves around. For a solid, that doesn't happen, which is why we like to say for a solid, it keeps its shape. Even if you toss it in the air, you catch it, you put it on the tabletop, it keeps its same shape. But a liquid, since they're only slightly hooked together, if you put that in another container, or no container at all, it just spreads out. It doesn't have enough hooking together to give it a solid shape. And so that's a solid, but that's a liquid. But whether it's a solid, a liquid, or here's a gas, and a gas just fills up the whole container. If I put a lid on this beaker and said, oh, I got the atmosphere in here, the atmosphere fills the whole container. I can take half the molecules out and close the container, and those half still fill up the whole container. So a gas, they're not hooked together at all. They just bounce around. And so I want to emphasize there is things different about a gas and a liquid and a solid. But what they have in common is the molecules are bouncing around. You might say in a solid, they're vibrating because they're just jiggling in place. Whereas in a gas, you might say they're ricocheting off. And in the liquid, you might say it's something in between. But my point to get us started here is to say whether I look at a gas, a liquid, or a solid, and so I'll look at the gas, I want you to have this mental picture. When something is cold, it means the atoms and molecules are moving very slowly. And so the difference between something cold and something hot is this. What if I warm it up? It looks like this. They travel faster. Did you notice that this styrofoam piece moved up really high when I picked up the speed, which was supposed to represent something hot? And that is where I begin this chapter. Thermal expansion. The difference between something cold and something hot is the amount of motion of the molecule. And so if you start with something that is cold, it'll take up a certain length. If you warm it up, because the molecules move faster and because they bounce off each other harder, they need more space. Thermal expansion. And that is the starting place for our thermodynamics. That warming something up, because the molecules got to move faster, they need more space. In fact, I think the best way to show that is with a little experiment here. And you'll recognize the name Fahrenheit. Said, okay, what if you took a metal rod? Now this happens to be a brass rod. So I've got this brass rod. And I'm going to then set this brass rod from one end to another. And maybe I'll mute this, I think, with the light bothering the camera. Yeah. All right, so I'll do this. And you'll see on this end, there's a little needle. And if I move the brass rod towards the far side of the room, you'll see it spins the needle in a counterclockwise direction. And if I move the brass rod towards me, it'll spin it in a clockwise direction. And you can see it's spun a lot. It doesn't take much movement of this brass rod then for that needle to move. And as a quick experiment to show thermal expansion, I'll start with the needle pointing straight up and say, well, what would happen if I warmed up the brass rod? And I claim, because of this thing called thermal expansion, that the atoms in here are going to hit each other harder and this rod's going to grow. It's going to expand over towards the far side of the room. which according to this needle then should move in a counterclockwise direction. So I'll give it a try. I'll just kind of go across the brass rod here, a little bit of heat, and hopefully the needle has moved. And so sure enough, the needle has moved. Now I should have put a little weight on here. Let me do that now, because when it cools down, it'll go the other way, and I need a little weight to make sure there's enough pressure on there to move the needle. And I want you to see as it cools down, the needle move back. And so we call this thermal expansion or cooling contraction, depending on which way you're warming things up. And so that's, like I said, the start of this chapter. It's got some interesting consequences. Here's kind of a fun one to do. This one, it's probably impossible to really see it well from your distance, is actually a metal, what shall I call this? A metal bar, a metal shaft, but it's actually two metal pieces. They're soldered together. It's hard to tell because they kind of look the same, but when you look down here where the flame hasn't been on it, you'll see it looks like stainless steel on that side and then brass on this side. And so if I draw a picture, I would say it looks something like this. I've got one metal strip and another metal strip. Let me try to give them about the same width. And I'll go ahead and hold it up here so that if I hold it this way, this is brass and this is steel, basically iron. And I make the same claim that if I warm this up, they should get longer. But here's the other thing I want to show you. Each material expands a different amount. They don't all expand the same value. And so if I was drawing a picture here, if I just took that metal rod there and said, okay, the metal rod has a length of L, and then when you warm it up, because the molecules need more space, it will grow by a delta L. Every little molecule would need more space. And so you might say, okay, well, why does it grow? Or what factors would go into it? And here's kind of our logic. That the reason this thing is growing really is how much did you warm it? I'll call it delta T, where T is going to stand on capital T for temperature. And so if I warmed it up, say 1 degree, it would grow a certain amount. But I think you can kind of see that if I warmed it up 2 degrees, that makes the molecules go even twice as fast as they did before, or I should say, increased twice as much. So if they were already going, say, 30, and I warmed it up 1 degree and they went 31, then if I warmed it up another degree to 32 and 33, anyways, they would grow by how much the temperature increased. So it's not a surprise that how much it actually expands by would be connected to how much I warmed it. Also, I hope it's not too much of a surprise that I should probably say, how much does it grow per unit length? Right? In other words, you're really saying that if I had a 1 meter rod, each meter would grow the same amount. But if I had a 2 meter rod, the actual growth of the 2 meter rod would be twice as much as 1 meter, because each meter would grow the same amount. And so I'm really saying here, when you warm it up 1 degree, every meter grows the same amount. Every little speck on the rod. And the big piece here is what we're going to call alpha, the coefficient of expansion. This is what I'm really getting at. This has to do with the material. This number, and I'll turn the overhead back on, would be a number that would be different for brass compared to steel. And so we call this the coefficient of linear expansion. And there's a couple ways you could rearrange this equation. Now, I like this one, where you put alpha by itself. And what you're really saying here is kind of an experiment that says, let's give a number that has to do with the material. In other words, if I came over here and warmed up this brass rod and it grows a certain amount, I know that part of the reason it grows so much is because how much temperature I warmed it up by. And so I want to divide by that. I don't want that to be part of my coefficient. I want my coefficient to just represent the material. So if I come over here and I measure how much did it grow, but I divide it by how much the temperature, I would really then be saying how much did it grow for every degree I warmed it up. And that's what I want my alpha to represent. I want my alpha to represent how much the material actually grows, not it grew because I warmed one twice as much as the other. The other thing I want to do is divide by the length of it, because again, if one rod grows more than the other just because it's longer, that's not part of the material. I want to factor that one out, so I want to divide by that. So I like this because here's what this is telling me. This coefficient right here is telling me how much does it grow per meter for each degree. Now, I'll look at some numbers here in our chart in just a second here, but I also like to write this equation in what I call the more practical form. And the more practical form is practical for two reasons. One, I'm not dealing with a quotient, so I'm just multiplying things. That tends to be a little more practical. But the other one is this is ultimately what I usually want. What I usually want here is to say, how much did it actually grow? Now, I would then say what determines how much it grows is really determined by the material. How long is the material to start with? In other words, how much material do I have? And how much did I warm it up? And so it's all three of these factors that determine how much it actually grows. If I warm it up a lot, it grows a lot. If I started with something really long, since every little microscopic piece grows by the same amount, it'll grow by a lot. But also, this factor, which is the material. And some materials will just grow more than the others. And so this is my way of saying we have a nice equation that we're going to use to calculate how much something grows. And of course, it depends on three factors. One being the material, one being how long is the material to start with. So in other words, how much material do you have? And the other one is how much did you warm it up? The more you warm it up, the more it grows. That's why I want to come over here now and turn this back on to your author. I started with looks like figure 10, because from an engineer's perspective, this is an important piece of the bridge. Without this, the bridge won't work. You see, when you build a bridge, I'll just pick on the Golden Gate Bridge, you're going to then, on one end of the bridge, hook beam after beam after beam after beam after beam. So you're going to have this long rod right here. This is long. And so on a warm day, it warms up. Now, fortunately still, this number's kind of small, but the beam is so long that when you put all this together, the bridge actually grows in length. And if you just took a metal beam on one side of the bay and connected it to the other side of the bay, and then it grows, what happens to that beam? Well, it'll now be twisted, something like this. You don't want to lock both ends of the beam. You want to give it room to grow. And this is a small bridge. This bridge, they don't give us really anything for reference, but what they've done is they've taken one side of the bridge and anchored it and extended it out. And as you get back over here, there's a ramp coming up to the other side, and they don't connect them together. That way, when the bridge grows, on a hot day, it'll look like this. And so this photograph was probably taken on a cold day, because now the bridge has pulled back like this. And you need room in your design, in your engineering, to account for that thermal expansion. How big is the bridge? This building, same thing. It's a big building. And when the engineers designed this, they had to give room for it to expand. And just actually outside of this door, along this wall, we have exactly that same structure. We have the building we're in right here, then it's separated from the other half of the building, and the two buildings come together. Now, in this case, they actually just left a gap, because unlike a bridge, you kind of want these little fingers, because you don't want to just have the bridge open up and have a big gap. You want someplace for the tires to still roll over. And so they've designed these little fingers here so that as it pulls back and forth, you can still drive over it safely. But for this, there's just the two building here, or two pieces of the building, and on a hot day, they get close together and there's not much of a gap, and on a warm day, they're further apart. And then sadly, they put a metal plate over on one side, and so all you can see is the metal plate kind of slide back and forth. That way things don't get in there and get squished on a hot day, and on a cold day it opens up and things fall in, and then they get squished on a hot day and damages the walls or damage whatever falls in there. But this thermal expansion is an important number, an important piece here. And this table then, as I was talking about, seeing how long it goes, is the piece of the puzzle that I want to show you getting started with. And so why don't I pick on brass, since that's what I was using up here. So here's brass. Notice it says 19 times 10 to the minus 6. Now notice the units say per degree Celsius. So here's what that 19 times 10 to the minus 6 means. In fact, I'll just kind of write it here on the board. Alpha for brass equals 19 times 10 to the minus 6 per degree Celsius. Now, you'll notice that there is no units of length, and that's because the change in length over the length would cancel it off. And so this means that a piece of brass will grow 19 times 10 to the minus 6 meters for every 1 meter for every 1 degree you warm it up. And that's a micrometer. So in other words, if I have a brass rod that is 1 meter, there we go, this is what I have. Oh good, it went back, and actually I probably missed it. It looks like it went back further than it was, so there was some sliding going on here. But I have my 1 meter brass rod. If I were to warm this up 1 degree, This is saying it would then grow 19 micrometers. This grows 19 micrometers for every 1 degree. Now, of course, you could imagine now a bridge that is made up of a lot of meters could actually grow quite a bit. And that'll be some of your homework problems and some of your example problems. You'll be surprised how much the Golden Gate Bridge actually expands, which is why they put one end of the bridge on rockers, so that as you get on from the San Francisco side, then on a hot day, the rocker will roll over this way and you can exit on the San Rafael side. But on a cold morning, you'll be like this. It'll be a little steeper off the edge of the bridge. Because of that extra, and I forget the numbers, it's actually an example problem they do. I think it's like a meter longer or something. And so the bridge has this thermal expansion. You ever wonder why the train tracks sound like clackety-clack, 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 clackety-clack? You ever wonder why there's a little gap? I mean, why didn't the engineers just put down a rail, and it probably was too heavy to make it too long, so I can understand why it has a certain length to it. But then why, when you put the next rail to it, do you put a little gap? Why don't you just put the next one right up to it? Answer: what happens on a hot day? The rail would expand. And that little slot in there is called an expansion joint. And so the two rails come together. So on a hot day, it'll close up. On a cold day, it'll expand out. And hopefully the difference between a hot day and a cold day is not enough that it'll have any troubles for the train to go over. But at the same time, if you had put them together on a cold day and then they warmed up and they pushed, they would need that room. And what would happen to the rail is it would begin to twist instead of being straight. And that would be a problem. And so those gaps are an important design. Maybe more practical to you guys is you probably drive a car. Have you ever checked, say, the transmission fluid? Have you ever checked the water level in the radiator? Both of those have little indicators that say, this is where the mark should be when it is hot. This is where it should be when it is cold. Because the reality is the volume of the transmission fluid will change. And so I know on mine, I've got this long dipstick and I stick it down into the engine and I pull it up and you look at the level of it. And if the transmission is cold, there's a little mark here that says this is where it should be when it's cold. But if you've been driving that car for a while, if your transmission is hot, this is where it should be. The transmission fluid is now taking up more space. And so to get the correct indication, you got to have the right volume. To get the right volume or the right size, you have to know what the temperature is. And that's what I'm getting at here. And so our first thing is a little thermal expansion. Now that I picked on brass, let me pick on steel. They probably don't list steel, but I bet they have iron. Oh, iron or steel. Okay. And so here they have a 12. And so I wanted to point out, notice the 12 is smaller than the 19. And so coming back to my little picture here, if I took a piece of brass and a piece of steel and I make them the same length, same length at room temperature. Did you catch that? They changed their length, so I got to say what temperature they're at. All right, so I make them the same length at room temperature and I solder them together. Okay, so that's what I have right here. And now I warm it up, what's going to happen? They're both going to grow, aren't they? But the same amount? No. Which one grows more? The brass. So after I warm this up, well, what's going to happen? Okay. If they weren't connected, I like what you're saying, you would get something that might look like that, right? You'd get the brass getting longer than the steel. Agreed. But the thing is, they are connected. And so what I will get are two pieces of metal, one longer than the other, but stuck together. And so that is what a curve is. Right? The one on the outside has a longer distance than the one on the inside. And mine is stuck together. So I will get this, not this. So let's see what happens. So I've got a nice little Fisher burner here, nice and hot. Turn on some gas, spark it up, and say, all right, let me find out which side is the brass. Okay, so here's the brass side, here's the steel side. Remember I said the brass is going to be on the outside, so I will put it in the flame and warm it up. And so to convince you of thermal expansion, here I have the two pieces of metal. We call this a bimetal strip, and it is now bent. And of course, what would happen when it cools down? They should be back to the same size, which they'd be in a straight line. And so it'll take a little while for this to cool down, so I'll encourage it a little bit. A little bit of water. And not really good for the metal. You can see why it's all beat up now, because I'm kind of rough on it. But see, now it's back to a straight line here. And so that's this whole idea of thermal expansion. In fact, it's why I brought some of these crazy things out here. Maybe a little bit of old school technology, but we have a bimetal strip that's kind of wrapped up in a coil here. And when you warm this, it will begin to unwind a little bit because it gets longer. Or when you cool it down, it'll tighten up. And if you have, and so this little bimetal strip this is a broken one. I don't know if you can see it on this one, but it's kind of behind this little dial. It's buried under there. But you can see what we call a switch. It's got a little liquid inside. And so when this turns one way, the mercury flows to this side. When it turns the other way, the mercury flows the other direction. And so this can be a switch in the sense that I can set my thermostat, and when it gets to a certain temperature in my house, let's say 65 Fahrenheit, it will move far enough over that the mercury will flow down, make two contacts of two pieces of metal, and that turns on the furnace. And so if it gets under 65, furnace goes on. Furnace starts to warm up the house. As the house starts to warm, the thermal expansion moves the bimetal strip and then eventually turns off the furnace. And so there's this constant on and off to the furnace using the bimetal strip. This one's even a little older school, but I like it because you can see it better. This one, here's the bimetal strip and here's the contact point. And so right now it's contacting it, but if I warm it up, you'll see it move backwards. And so I'll use the flame here to say, all right, let's warm this up a little bit. And so try to warm it without burning my hand here. But it won't take too much heat for you to see it. Can you see it moved far enough out here? Yeah. And so see that opening right there? It's quite a bit open right now. And there's not any contact. If I cool it down, you'll see it is now moved over and it's touching. And so that would turn on the furnace. Well, you can see this in a lot of features. Well, what was the other one I had? Oh, I guess I had an old iron here. And so if I was ironing my clothes, you know, I'd have a little dial here on top, and I'd set it for medium heat. Because right inside here is a little bimetal strip. And if it gets too cold, the bimetal strip moves up, makes contact, and it's plugged in, and so electricity would flow through, warming up the iron. Once the iron gets to a certain temperature, the bimetal strip would expand, breaking the contact, and the electricity would turn off. Now, it's still plugged in, and on top it still says on, but it's not making contact, so it's not heating up my iron anymore. So my iron doesn't get too hot, it just shuts off for a little bit. And of course, eventually it cools down, and so the bimetal strip goes down, and so it's constantly making contact, and it's on for a couple of seconds, then breaks contact, and so it's off for a couple of seconds, and then on, and then off, and then on, and then off, and so roughly keeps the same temperature as I'm ironing the clothes. I don't have to plug it in or not. The bimetal strip uses the advantage of turning it on and off here. And of course, I could also use this as a thermometer. And so here I have, I guess this is a cooking thermometer, and here is what I'll just call an everyday, ordinary thermometer. This reads, you know, normal temperatures. This reads hundreds of degrees Celsius. And so if I was, you know, wanting to measure temperature of the melted chocolate, I'd put that in the chocolate dip there, and inside here is a bimetal strip, and it would then wind and unwind, and then the dial on here would move. And so we can take advantage of that. And now, let's keep going with this, because if you look at your author's next picture, picture 11, he points out something quite interesting here, that if you warm, I'll leave that on for a second. If you warm up an object and its length expands, won't its surface area and volume expand also? And so in this picture, he's trying to say, and here's a kind of a three-dimensional, that's probably a better one than this, but he says if it expands in its length, and it expands in its height, and it expands in its width, or if you're just looking at the front surface, if it expands in its length and its height, wouldn't its area expand? And wouldn't its volume expand? And shouldn't those be connected to this? And sure enough, they are. Your author says, look at this for a moment. If you have a surface area that maybe has a length and a width, and then you warm it up, and so I will just say your starting area is length times width. But if you warm it up, it is now going to be L plus delta L, and it's now going to be width plus delta width. And if we use this idea, you would have L plus alpha L delta T, and the width would be the original width plus alpha times the width times delta T. If you'll notice, there's an L in each term, there's a W in each term, so I can factor those out. And then I would have 1 plus alpha delta T. And I would actually have that for both terms, and so it would be squared. Now, if you'll go ahead and let me use a little bit of mathematics from your algebra class, what is a plus b squared? Isn't it a squared plus 2ab plus b squared? Okay. So a squared would be 1. So 1 times 1. 2ab would be 2 alpha delta t. And b squared would be alpha squared delta t squared. And let's look at this term by term. The first term, L times width times 1, I would call this first one the original area. So these other terms must be how much did the area grow? See, because this is the original area, length times width. If you look at the second term will be 2 alpha times length and width times delta t. The second growth term, or this last term here, would be alpha squared compared to alpha. Ooh. Let me just ask you, was alpha a big number or a small number? It's really small, right? Those are all times 10 to the minus 6. So if I square it, it's 10 to the minus 12. Let's just say it's so small we're not going to worry about it. How about that? And here's what I'm getting at. What I'm trying to get you to see is that if you wanted to know how much the surface area increased by, you could just say it's this piece right here. That is, the change in area would equal 2 alpha times the original area times delta t. Doesn't that look a lot like delta L equals to alpha L delta t? So in other words, if its length grows, its surface area grows. And the amount it grows by would be a factor that is twice the linear growth. And so that's why we could say, hey, if you know this alpha, if you know how much brass grows in length, you also know how much the surface area grows because you just multiply it by 2. And so we'll just take the original area, multiply by twice alpha, multiply by how much you warm it up, and that's how much the surface area would grow. Now, since this is a homework problem for you, I will leave this for you to figure out. How much would the volume grow by? Do you see that what I would have is just another term right here? I would have maybe the height times delta height. I would then just have height plus alpha original height delta t. And so I would have length times width times height. And this one can factor out an h. And so I would have an h here. And I would have a 1 plus alpha delta t, and instead of squared it would be cubed. Well, here's where maybe the math gets a little harder. Do you remember what a plus b cubed is? I'll let you think it through. But I will tell you this. The first term will be a 1. The second term will have a 3 alpha in it. There'll be more terms, but all of them will be small. All of them will have like an alpha squared or an alpha cubed. And so what you will get is 3 alpha times the original volume delta t. I'll even say this, that for a lot of problems, we are interested in the volume it grows So we give it its own name, beta. Alpha, beta, gamma, delta, epsilon, eta, zeta, theta. I mean, we just go right down the Greek alphabet. We're not real creative. We're just silly physical scientists. All right, but here's why I wanted to say that. If I come back to a problem like this, and I say, how much bigger is it? We got to read that problem careful, because are they asking how much longer is it? Are they asking how much the surface area is bigger? Are they asking how much the volume is bigger? And that might be the biggest challenge in the problem. Okay, what growth are we talking about? Because the railroad line, I just really care about its length. The fact that it gets a little wider, it's not much, and it's really not relevant. It still works. I don't really care how much the railroad gets wider. And if it gets taller, I don't really care about that. So working with the railroad, I just want to know how much longer it gets. However, going back to the car, if this is my transmission fluid, or if this is the water in the radiator, I want to know the volume, how much the volume gets. And that's why when I pop the hood on my car and I see the radiator, I see this plastic container, and they call this an overflow container. And it's about half full when I start my car in the morning, but after the car warms up, after the water gets hot, the volume expands, and the reason it's called an overflow tube is the water will come out of the radiator, it'll go down that little rubber hose, and it will go into that overflow container, and the coolant goes into that container. And so if I look after I've been driving for a while, that level has now gone up because there's more volume. And so what I'm interested in is the volume of that. And of course, the reason you put it in a little airtight, vacuum-sealed container is because then when the car sits in the parking lot and cools down, it'll create a siphon and pull that back into the radiator. And so the coolant can come out when it expands, but it can go in when it contracts. And so I have a well-designed car that can take account for the fact that the coolant used to cool my car has to have room to get bigger and smaller. And so it does. And so the engineers were smart enough to add that to my car. And so there's the part. Am I looking at area or am I looking at volume? Well, coming back to this table, you will see that back here at the top that the author had actually said, I'll just pick on aluminum. Here's aluminum, and it says aluminum has 25 times 10 to the minus 6. That's the alpha. That's the linear coefficient. But it has another column called beta. It's kind of a waste of space because wouldn't beta just be 3 times alpha? And sure enough, 25 times 3 is 75. 19 times 3 is actually 57. 17 times 3, 51, and so forth and so on. So many charts don't even list the beta. Everybody knows it's just 3 times alpha. Except, we got to be careful with liquids. See, liquids, remember our discussion earlier? Liquids never grow in a straight line. They only grow by volume. It makes no sense to talk about a linear expansion because a liquid will flow in whatever shape it's confined in. Which is why you'll see when you scroll down here and you get to the liquids, the author doesn't even list anything for the alpha. It, again, makes no sense to talk about an alpha for a liquid. Or for a gas, because they just fill up the container. Actually, even talking about a beta for a gas makes no sense. It just always fills up the container and then the pressure changes. But if you stick to a certain atmosphere pressure, then you could kind of put a number there. But again, that's what your author is after. Well, let me come back to another fun experiment here. You'll see that I have a ring and a sphere. And the sphere has the same diameter as the inner radius of this ring, right? It just barely fits through. And hopefully this first step doesn't surprise you given everything we've said, and that is if I take this sphere and warm it up, it takes a little while, so give it a chance here, but it should get bigger, right? And the radius should get bigger. And And that would be a linear expansion, which would make the volume get bigger, so that would be a volume expansion. And I guess the surface area would get bigger. So all those are getting bigger according to this math. But to show you it has gotten bigger, then it won't fit. If I cool it down, it should now fit. Now, I think maybe the hardest one to really understand, until let me rewarm it, is to say, what if I have a hole in my material, the ring? What if I warm up the ring? Will the hole in the ring get bigger or smaller? Well, let me give it a try here. So I'm going to rewarm the sphere to the point it doesn't fit. And then I'm going to warm up the ring. Now I'll keep the sphere in here so the sphere stays hot, so the sphere's bigger. But remember my question. My question is, will the hole actually get bigger or smaller? And I want to convince you it gets bigger. I think people's natural reaction is to say it gets smaller. Most people say it gets smaller, but it does not. And so if I have them both warm, not quite there yet. But there it goes. The hole actually gets bigger. Again, I'll leave the sphere warm. I'll cool down the ring. And when I cool down the ring, the hole actually gets smaller. Okay? So cold ring, warm sphere, doesn't fit. And of course, if we go back to room temperature, ooh, this thing's really warm. Okay, cool it down. Now it fits. And the best way, I think, to explain that is with a picture, and that's what your author is attempting to do here. We'll go back to that picture 11, but your author is trying to say that this may seem kind of weird to many people, but if this is cold and this is hot, most people get the idea that if this is the length when it is cold, then it grows when it is hot. They have no problem with the length or the height growing. It's the hole in the middle that is a little bothersome. But I'm going to explain this. Isn't the hole in the middle really defined by the length of the material down here that then makes the hole? And so it's this material here that then grows, making the hole bigger. And it would do the same thing in this dimension, making the hole bigger. Maybe another way of saying the same thing is if there wasn't a hole there, if there was just metal actually in there, that metal would get bigger. And so the metal around it gets bigger to make an open space for that metal. Here's the neat thing. If somebody were to ask me, how much does the diameter of the hole grow, I will think of it as being made out of brass and asking the question, how much does the brass in the hole grow? Even though it's a hole, it's not made out of brass. And that's the trick I want to point out here. Those are the two things I wanted to emphasize, is that when you are asked to calculate how much bigger a hole gets, first of all, notice it gets bigger when you warm it. And second of all, when you go to calculate it, just pretend there's material in there. Because usually the question I get from the homework is students ask me, they said, hey, when you calculated how much bigger did the diameter get, you treated it as if it was made out of brass, but it's a hole. A hole is not made out of brass. And I need to say, well, yes, but the hole is made from the brass around it. And the brass around it expands in the same amount that if there was brass there. So I know there's not really brass in the hole, but that's how you're going to calculate the expansion when you have an opening, when you have a hole. And so it's actually fairly easy to do, but it does take a little justification. And that's why I wanted to spend some time here justifying it. Now, I also should probably say something that your author does a good job in the figure, looks like he's got figure 12 here. Be very, very careful with what I am saying versus a phase transition. Here in figure 12, your author shows you a graph of the density of water. Okay, so let me come back over here to my model of water. So here is my water. Okay. And I have been saying for the last 40 minutes that when you warm something up, it gets bigger. And when you cool it down, it gets smaller. However, when you freeze something, you're changing phases. You're not just making them go slower, you're actually changing how they're hooked together. And so if we imagine this to be ice, and this liquid water, if this was started off as warm liquid water, so on my graph, if I start off at, well, I don't know if I'd call that warm, but 12 degrees Celsius, and so this is shaking around at 12 degrees, and we cool it to 11, and then we cool it to 10, and then we cool it to 9, wouldn't it start to get smaller and smaller? It would contract, which means its density would go up, right? It would be the same number of molecules. Density is mass per volume. So its volume would go down. And as its volume go down, its density would go up. And so your author is trying to say, as you cool it down, its density goes up, and it goes up, and it goes up, and it goes up, and it goes up. But at 4 degrees, from 4 to 0, and even when it gets colder than that and freezes, we need to be a little careful. Because when you go from something that looks like this, a liquid, to something that looks like this, even if they're going slower, can you see the spacing between them? And you don't have that spacing here. So that's the behavior of ice. Ice in a liquid form, the molecules are real tight together like this. When they freeze and become a crystal, they look like this. And because there's spacing between them, the density of ice would go down. And it could go down dramatically. In fact, going back 2 chapters, what did we say about something that sinks and something that floats? Didn't we say if it floats, it has to have a density less than the liquid it's in? Does ice float in water? Yeah, so what does that tell you? It's a lower density. And so if you take what I'm saying the wrong way, you'll think ice should have a higher density. You would think, well, it's colder, so it should get smaller. And I would say that's true if we're only looking at the molecular motion. It changes once you start hooking them up in a different pattern. In other words, the size of the ice has nothing to do with the speed of them anymore. It has to do with the way they're hooked together. And so the density of ice could have been more, could have been less than the water. It happens to be less, which is a good thing, especially for you guys in the life science, because what that means then is if you have a lake and the air gets cold, the cold air cools the water, and the coldest part is the top. Of course, it now sinks to the bottom, and so the whole lake starts to cool down until 4 degrees Celsius. Because at 4 degrees Celsius, the density starts to get bigger again. It starts to form ice crystals. And now things colder than 4 degrees go to the top. Then it freezes at the top, but it's still a liquid underneath. And so all the life can make it through the winter. It's very cold outside. The ice is very thick. You might get 6-8 inches of ice on the top of the lake, but all of that down below is now protected from the cold air, and it won't freeze during the winter if the lake is deep enough. And life then can go on. If ice sunk, if this wasn't true, it would be totally weird in the terms of our life, because you would get ice forming at the top, and if it was more dense, it would sink to the bottom, which now the water is exposed to the cold air, making more ice. Each time it would sink, and eventually the whole lake would freeze up. And those fish would all die. And everything living in there would die, wouldn't make it through the winter. And so, fortunately, for the life science, ice actually has a lower density. It actually floats. And so that's our good thing. So again, I just want to be careful about what I'm saying here, especially for you guys in the life science here, because you have probably studied already a lot that the ice is low density. That's why it floats. That's our Archimedes principle. And of course, that's why we can sustain life throughout the winter in Minnesota when all the lakes freeze over the top, but the fish don't die. And so again, when it comes to this thermal expansion, I just want to be careful. Now, maybe we should call it a quits, because as you will notice, I've been talking about temperature, and so now is a good time to talk about temperature scales. Sometimes I mention Fahrenheit, and sometimes I mention Celsius. So far I haven't mentioned Kelvin, but those are going to be the 3 temperature scales that we need to work with, which you guys are probably somewhat already familiar with. All right, well, we'll call it quits here for today and pick this up on Monday after the test. All right, 9:30. All right, hey, welcome back here. Let's continue where we left off. And just to remind you where we left off, we were in chapter 13, and we had done, I would say, one part, maybe a third of it, because there's 3 big things to cover here in chapter 13. And the first one was that thermal expansion. And so hopefully we'll have some time to do some examples and jump back to that. But the second thing I want to do is then to talk about temperature scales. And I will go ahead and then begin by saying, and let me blacken this out here for a second. But one of the areas of thermal expansion that I didn't mention explicitly was a thermometer. And a thermometer uses, and this one happened to use mercury, but some kind of liquid, where you put the liquid then, say, in warm water, and then it gets hot. And the molecules bounce around. And they need room to expand, and so what they do is they go up the little tube, up the capillary tube. And so that's why we say the thermostat, or the temperature rises, because when it gets hot, they move faster, and they need more space. And so this was Fahrenheit, and well, maybe more Celsius and Fahrenheit's idea of making something that can actually record a temperature. And so they use the principle of thermal expansion. And so what I want to do is introduce you to, if you haven't already, the 3 main temperature scales that we like to use. And this will give us a understanding of how they were developed. And then, of course, more importantly, is then the advantages of each one, and then switching from one to another. And so as I said, I like to do the thermal expansion first, I noticed your book actually does the temperature scales first and then goes over to thermal expansion. But I think that understanding the thermal expansion can be done conceptually with the molecules bouncing around, but then that gives me a reason to explain why we use a mercury thermometer or an alcohol thermometer. Both alcohol and mercury are good liquids that expand quite a bit when you warm them up, and so that's our idea. So what I'm going to do here is I'm just going to put what is going to hopefully look like to you 3 thermometers, and hopefully they look a lot like the one I was just holding up. And we'll talk about the oldest scale first, the Fahrenheit, which is not one we will focus too much attention on, and you'll see why. But very common here in the United States. And then the Celsius scale, and then what I'll call the best scale, the Kelvin scale, as you will soon see and hopefully understand why. All right, let's start with Fahrenheit, and in the interest of time, maybe I won't go through the whole story, but it is kind of a fun story of his thinking, and here's kind of the place I want to start. You saw this earlier on, and I'll show it again. But if this rod moves, you can see the needle spins. And the rod doesn't have to move much for the needle to move. I used it as a way to show you thermal expansion. And Fahrenheit had the same idea. He said, let's kind of get some kind of markers, if you will, some kind of what we call standard reference points. And so if you could imagine, and I won't actually do it, but if you could imagine taking a bucket of ice water, so here's my ice, and boiling water, and so I don't quite have boiling water in this hot coffee pot, but I've got some pretty warm water. In Fahrenheit's place, you could imagine him hanging him from the ceiling, so he goes out and gets a bunch of snow and puts some water in there, and then he makes another bucket and puts a fire under it. So he's got both ice water and boiling water. And that's the key. And that's the first thing I want to put over here, is because our reference points are going to be ice water and boiling water. And Fahrenheit experimented with some other options, but ultimately settled down on something that was very easy to repeat. Something that, he could just write, hey, here's the procedure, and you don't have to be here in England, you can be in Germany, just pick up some snow in the winter, and you can make a thermometer here. And obviously boiling water is really easy too. Everybody's got water, everybody's got wood or coal, and you just make a fire. And so Fahrenheit does something like this, and like I said, it's kind of a long story here, so without going quite into every step of the details, he does something like this. Maybe I'll start with the ice water. So he takes a little tube and he puts it through here and he runs ice water. So if you can imagine this ice kind of running through here, getting it really, really cold, you could imagine from the last lecture that it would then shrink. And what would happen is the needle might move back a little bit. Now, in my case, I didn't actually run the water through there, but again, let's pretend I did. Because then he's got this clever idea as his starting point. And so he puts the needle straight up. Okay? Then he switches it. And he takes off the ice water and he puts in the boiling water. So now the boiling water goes through. And again, I won't do boiling water, but I will do what I did last time, which is to say, okay, what if I added heat to this brass rod? And this is our thermal expansion. That is, the atoms would start to move faster and faster and faster. And you can see then the needle moved. And he set it up with a combination of how long the rod is and how big the shaft is, so that when he went from ice water to boiling water, that needle would go halfway around the circle. And so it only made sense to him to say, let's call these, because he's not really thinking of temperature, he's thinking of a measurement on a protractor, 180 degrees. I mean, a half a circle is 180 degrees. So he calls ice water to boiling water 180 degrees. Makes sense, you got half a circle. But I always find it interesting then that now, hundreds of years later, we kind of associate degrees with temperature, not a protractor. Oh, maybe we do a protractor too. But now we've got degrees that are kind of confusing. It's like, wait, are you talking about degrees on an angle? Or are you talking about degrees on a temperature scale? But in his thinking, it was just the angle on degrees, on a temperature scale. Now, he does one more thing, which sounds kind of weird, but it's important to understand, is he says, you know what? We can make things even colder than ice water. And maybe you've done this if you've ever tried to make like homemade ice cream. Because you know that milk doesn't freeze with just regular ice. It needs colder than that. Do you guys know how you get stuff colder than that? Do you know how to make ice cream? No? 4th of July is coming. You're going to make some homemade ice cream? So you mix up all the ingredients of the ice cream and you put it in a container, and then the outside you put the ice, and so you get ice water. But to get it even really cold, you then add salt to the ice, and the salt dissolves. And as you go through your chemistry, you'll learn that salt is an endothermic reaction, and so as it dissolves the ice, it gets colder and colder and colder and colder and colder. And it can get really cold depending on how much salt you put in. And so making homemade ice cream, you put in a lot of salt because you got to get milk to freeze. And milk doesn't freeze until quite a bit lower than the temperature of ice. So Fahrenheit knows that. So Fahrenheit does one more thing, and if you can imagine a third bucket, this third bucket, he first puts the snow in it, and then he puts the water in it, then he puts tons and tons of salt and stirs it, and the temperature goes down, 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 down. And so then he runs that tube, and of course the dial goes back to straight up. That's what you would call the ice water, but it even gets colder than that, and so it moves back. And he measures that angle. And that angle comes out to be 32 degrees. And so he says, okay, then this is dropping down another 32 degrees on his protractor. And again, you got to remember, he's not thinking of this in terms of a temperature scale yet. All right, but maybe this will help us understand then Fahrenheit's thinking, because then he goes, well, let's make a scale out of this, and why don't we then call the lowest point I can get 0. Kind of recalibrates, what is an angle of 0. So realizing that he can make things really, really cold. Come on in. Yeah, we're just waiting for you now. But he realizes you can get it really, really cold, so he calls this 0 Fahrenheit. And then using his little protractor, this then becomes 32 degrees Fahrenheit. And then if you add half a circle, 180 degrees to this, you get 212 degrees Fahrenheit. And so probably most of you already know the temperature scale in Fahrenheit, but if you're one of my international students, you might not. And you're not familiar with the Fahrenheit scale. But that's the Fahrenheit scale. And so what I want you to get out of this, if you don't already know, is that on the Fahrenheit scale, ice water is 32 degrees Fahrenheit. Boiling water is 212. 0 is really not important, so don't worry about it. But if you want to know, 0 is what you would get if you mixed a lot of salt and ice and water together and stirred it up and got it as cold as you possibly could. And so that's kind of the meaning behind them. And then notice we'll label them with degrees Fahrenheit. Okay, well, if that made sense to you, let me continue on. because Celsius comes along and says, let's improve this a little bit. Let's make a better scale. And the biggest problem with this scale is it's based upon a protractor. It's based upon 180 degrees. It's also basing 0 on something that's really not important, salt water and ice water. We just don't really care too much about it. Plus, Fahrenheit used it because that was the coldest he can get it, and Celsius is going, well, I've got better things that can get it even colder than that, so that 0 is kind of pointless. So Celsius does two big things. The first one is to say that the ice water and boiling water are great reference points. So thumbs up to Fahrenheit on that one. We'll keep that. But the fact that the ice water and boiling water is 180 degrees probably could be improved if we divide it into 100 pieces. And so it's more of a base 10 that the whole metric system is designed around. And so we no longer like those things that have like 12 inches to a foot or 3 feet to a yard, and the list goes on and on. Okay. So he says, let's do it on a base 10. And so it made more sense to divide it into 100 pieces. Now, keep in mind, because this is going to come into the math in just a second, that if you have 180 of them between ice water and boiling water, and then you reduce that to only 100 of them, then these are bigger. These are bigger by almost a 2-to-1 ratio, right? 180 is not quite 200. But what this is really saying then is if you go up 1 degree on the Celsius scale, you're going to go up almost 2. You're going to go up 1.8 degrees on a Fahrenheit scale. And so a good number to keep in mind is 2 degrees on a Fahrenheit scale is the same as 1 degree, or very close, to 1 degree on a Celsius scale. And so hopefully that's one of the things you see right away in this comparison. Now, the other thing that Celsius wants to improve upon is where you call 0. Since salt water was kind of a poor choice, but ice water is a great reference place, why don't we call that the 0? And so Celsius changes it and calls this 0 degrees Celsius, making then boiling water 100 degrees Celsius. And so that's, I would say, is a nice improvement. But what I want you to get at it, if there's anybody who doesn't know the Celsius scale, is that 0 would mean ice water and 100 would mean boiling water. So 100 Celsius corresponds with 212 Fahrenheit. 0 Celsius corresponds with 32 Fahrenheit. Okay. Now, if you just let me pause here, you can see that there is clearly a mathematical connection, right? If you came over here and said, okay, what is the temperature on the Fahrenheit scale compared to a Celsius? Well, I think the best way to do this is to kind of just do a comparison. Maybe a mathematical plot would be good. What if I put like the temperature on the Celsius scale on the x-axis and the temperature on the Fahrenheit here, and you can kind of see when Celsius is 0, that must correspond to 32. That's where the ice water is. And then they would increase at the same rate with a slope that would be their ratio. And so that is when you get to 100 on the Celsius scale, you should get to 212, which is an increase of 180. So the slope of this would be 180 over 100. Some people reduce it to 9/5. I don't personally like to reduce it. I know that kind of helps mathematically, but it takes away from the meaning of 180 divisions on the Fahrenheit scale compared to 100 on the Celsius scale. But it lets me do the math. I mean, if you think about this as y equals mx plus b, I just have a line. I can go from one to the other. So on the vertical axis, I have the temperature on the Fahrenheit scale. The slope is 180 to 100 on the Celsius scale, and the intercept is 32 degrees. So there's the meaning in the mathematics going from one to another. And so you'll be asked on the homework to say, hey, I have a temperature on the Fahrenheit. All right, put it in. And then you can calculate it in the Celsius. Or the other way around. I have the temperature in Celsius. Okay, put it in and calculate the temperature on the Fahrenheit. And so if you know one, you also know the other. In fact, your author takes the time to write out both equations. I'll save a little bit of time and not do that. I think it's kind of a waste of effort to do that. But he gives you a whole list of all, looks like, all 6 possibilities. And the one I'm currently talking about is right here. How do we go from Celsius to Fahrenheit? Notice he reduced it to 9/5 and kind of loses the meaning behind it, and we can have that one. Now, if you rearranged it by putting the 32 over to there and bringing the 5/9 to the other side, you would get this equation, so you can put it in there and there. But to me, those are the same equation. So in order to really save some mental power, I'm going to say don't try to memorize both of them. Just kind of memorize a line. This is a line. This is the slope of the line. This is the intercept of the line. If you understand where the Fahrenheit came from and how the numbers derived, you can almost just, write this down without much thought. However, that's not really what I'm asking you to do. I'm asking you just to be ready to convert, and you have a nice little table from your book, and of course, on exam number 3, you might be asked to do that and convert from one to another. Anyways, I'll keep going here. There is one thing that Celsius, I think, really messed up on, actually 2. But one, I just kind of find it humorous that, his big approach was to put it in a base 10. Get away from this protractor. And he still calls them degrees. And so even to this day, we still say that, yay, today's temperature is 24 degrees Celsius. It's like, okay, degrees. Anyways, and so we're kind of stuck with degrees now, having a double meaning. It means not only just an angle, but also on a temperature scale. Fortunately, as we go to Kelvin and we improve the temperature scale, Kelvin says, stop with the degrees. Just don't put the word degree in there. Should have never been there for Celsius, and so we're not going to have it when we talk about Kelvin. Although I got to admit, it's hard sometimes. I mean, somebody asks me the temperature, and I go, oh, it's 300 Kelvin. It just doesn't seem right. It feels like I want to say it's 300 degrees Kelvin. And that's not what you're supposed to say, but yet we still do it. It's just kind of bred inside of us with Fahrenheit in degrees, and then Celsius kind of following that. It just seems like Kelvin should do the same thing. But Kelvin's pretty adamant about it. He goes, don't say degrees. That is not how I want to set up the temperature scale. So that's a big thing over here, and you will soon see then that Kelvin also says there's a lot of good. For example, the ice water and the boiling water that was originally used as a reference from Fahrenheit are great. Let's keep that up. So Celsius does that. Kelvin does that. Let's not change that. Kelvin also says it's really nice to have 100 markers between ice water and boiling water. Notice I said markers, not degrees. And that's like the one thing that Lord Kelvin is going to do. He's going to say, look, no, let's not call them degrees anymore. Let's just say that there's 100 divisions, 100 markers. There's a change of 100 Kelvin when you go from ice water to boiling water. Just don't say degrees. Okay. But the biggest thing that is the improvement on the Kelvin scale is, and we'll have to come back over here to show you again and ask you guys, what's the difference between something hot and something cold? Well, I've showed you a few times. This is supposed to be my little model of something that is cold. And so when it's cold, these BBs are bouncing around. And when it gets hot, they go even faster. So Lord Kelvin begins to understand we're going to call this the kinetic theory, that everything in the world is made out of little tiny atoms and they bounce around when you warm them up. And so Lord Kelvin is going to say, calling this point 0 is probably not the best idea. And here's why. Because you can get colder than 0, which means the molecules go slower, and the molecules go slower, and the molecules go slower. And he realizes that if you keep getting something colder and colder and colder and colder, meaning the molecules go slower and slower and slower and slower, at some point they're going to come to a stop. And so he realizes that there is something called absolute 0, meaning there's no motion to those molecules. And he argues that the best place, no matter how cold that is, way down here, that's the place that he wants to put the 0 on his scale. Because if you put 0 there, then you have a scale that the numbers on the scale correspond to the motion of the molecules. The other scales don't do that. And that's why I would say, of all of these 3 scales, by far the best one is the Kelvin scale. Because Kelvin scale is the only scale where the numbers actually relate to physics of what's going on. The physics of the molecules actually moving. Okay? None of the other ones do that. And so that's his argument. And that's the big improvement. However, what he doesn't know is how cold is that? Where is it? And so he runs a little experiment like, well, you guys who are in person, we did last Wednesday. We did that absolute 0. And we put things in boiling water, then we put them at room temperature water, then we put them in ice water, and we even went one step further and we put them in dry ice. However, the molecules were still moving pretty fast at that point. So the way we found absolute 0 is we made that graph. We extrapolated the motion until the pressure came out to be 0 to find out where is this point that they stop moving. And of course, we were doing this on the Celsius scale. So the corresponding on the Celsius scale is they would stop moving at negative 273 degrees Celsius. And so that's what we refer to as absolute 0. Meaning, you can say it's negative 273 on the Celsius scale, or you could say 0 Kelvin. Again, notice I didn't say degrees. So 0 Kelvin corresponds with negative 273. So that's the big improvement on the Kelvin scale, is that 0 on the Kelvin scale corresponds with 0 motion. And that means all the numbers that are on this temperature scale have to do with motion. And most of the physics that goes on has to do with the motion. And so it makes the most sense then to write an equation that has the temperature on the Kelvin scale. All right, well, let's see if we can do a translation of the math. And it's actually pretty easy, because if you're going to make the divisions on the Kelvin scale the same size on the Celsius, that means going down, and you went down 273, then over here, if you go up, then ice water would be 273 Kelvin. And then 100 more for boiling water would be 373 Kelvin. So probably one of the bummer parts about the Kelvin scale is ice water and boiling water, which are so important, are not nice round numbers. They're not like a 0 or a 100 like they are on the Celsius scale. They're also kind of big numbers. You know, that means room temperature is probably right around here at 295 Kelvin. So if someone says, hey, what's the temperature in this room? And you say 295 Kelvin. It just doesn't feel right. It doesn't sound right. 295 Kelvin? Oh, that's pretty hot, isn't it? No, it's just 22 Celsius. About 70 Fahrenheit. Like, oh, might be 68. We can do the math there, but you kind of get the idea. Now, fortunately, it makes the math really easy to go from this one over to this one. All you have to do is change it by 273. So that means if you have the temperature on the Celsius scale and you add 273, you're going to get the temperature on the Kelvin scale. And I suppose we could kind of do a graph over here, but again, hopefully you'll see the graph is kind of saying the same thing. The slope would be 1, because you would have 100 and 100, and then the intercept would be the 273. And so sure enough, if you come over here, I'm sure your author shows you this formula. Here it is. And then he rearranges it for the other direction. I'm going to suggest don't try to memorize both of them. Just run through the math when you need it. If you know it in Kelvin, put it in here and solve for Celsius. If you know it in Celsius, put it in here and solve for Kelvin. And so these are the two biggies. And you don't even need the other one that would say, hey, can I go all the way from Kelvin to Fahrenheit? Sure, we could kind of merge this equations together, but why don't we just do two steps? If you know it in Kelvin, start there and get it in Celsius. Once you get it in Celsius, put it in here and get it in Fahrenheit. Or the other way around. And so he's got these other ones, Fahrenheit to Kelvin, which is just the combination of these other ones. So I'll show you all 6, and if you prefer just to look at the table and find which one you need and plug and chug into there, go ahead. But I find this to be a better option. There's only 2 equations. They're both really easy to kind of work out in your head from scratch. And so if I'm just, I'll do it, I'll say, oh yeah, this would be the formula. Yeah, here it is. And then I can go from one to another. Because if I memorize a bunch of stuff, I'm just going to forget it. And this is a good chance to say, I haven't said in a while, physics is about knowing how to apply a few fundamental principles to explain a universe of phenomena. And so you saw that, right? We had Newton's 3 laws and then the 3 conservational principles, and that explained all of our motion. We got conservation of linear momentum, conservation of angular momentum, conservation of energy, and Newton's 3 laws. And it's like everything else just kind of was deductive reasoning from that. And so, you want a hint to study and prepare for exam number 2? Newton's 3 laws, 3 conservations, nothing else is more needed, just figure out the details. But hopefully you've practiced those and practiced them a lot, because the 90 minutes is not a time to learn them during the test. You got to go read the question and go, oh, okay, I know how to do that. Oh, I know how to do that. Well, like I said, this chapter has 3 big pieces, and that's the second one. Thermal expansion was the first one, and then this is our second one, converting from one scale to another. Now, the third and last piece of this chapter is to study a little more physics about gases in particular. And so we call this the ideal gas law. Now, let me again emphasize something that we did on the last lecture, and I probably should have emphasized it a little bit more. I know I did emphasize it some, but I was trying to say, okay, this is the visual picture of a solid. And if you take a solid and you warm it up, it begins to shake. And so it gets longer and it gets taller and it gets wider. And so its volume increased. And so I came over here and said, all right, we have this nice little formula. We called it thermal expansion. We said the change in length would equal to some constants that had to do with the material times the original length times the delta T. We even did volume and we did area. Let me not repeat all of those. But what I was trying to say is in that little chart, and I believe for your author, he puts all these numbers of the different materials in table 2 here as he talks about thermal expansion. And so, let me just come back and pick on aluminum. So we would look this up for aluminum and we would say, okay, now we know how much more aluminum gets bigger for every degree you warm it up. And so we could do a calculation. We said then that if you multiplied that number by 3, you would get the beta. And so if you had a liquid and you warmed it up, and it doesn't have to be a liquid, it could still be a solid, but how much the volume increased would then be a calculation based upon beta. In fact, maybe I said I wasn't going to put the equation here, but I'm going to come over here and do it anyways. Let me not do the area, but just the volume. And so this is beta times the original volume delta T, where beta it's a homework problem to show that it is 3 alpha, and I was showing you how the area would increase. But if you remember, I also pointed out that it's probably not a good idea to think about this chart applied to gases. And so I'm going to go down and pick on your author a little bit, because down here at the bottom here, your author actually gives you an expansion coefficient for a gas. And I want to emphasize that really those equations should only be applied to solids and to liquids. The problem with a gas, and so we'll come back to our model, is as it bounces around, the molecules take up the whole space. And if you talk about their size is not just based upon what temperature they are, but how much pressure you put on. See, if I take this and I squeeze it down, I could change its volume by just more pressure. It has nothing to do with the temperature. And so the gas, because it has space between it, actually depends as much on the pressure as it does the temperature. I mean, you could kind of see the temperature change. Like here's cold, small volume. Here's hot, big volume. And if you left the pressure the same, then you can actually talk about it. And that's what the author is trying to say here. He goes, well, if you leave the gas alone and you leave it at atmospheric pressure, okay, that's what he's trying to say in here. But I'm trying to go one step further. I'm trying to say we don't usually do that with a gas. With a gas, we usually change its pressure and we change its temperature. And so its volume changes with both of those. And so we need something more complicated for a gas, something more advanced, something that depends not just on temperature, but also depends upon pressure. And so that's what your author does here in the second half. He says, all right, let's take a look at a gas. And so let's look at gases. And we call this the ideal gas. An ideal gas is this model of these atoms bouncing around and hitting each other. So it would be the same for nitrogen, as oxygen, as chlorine, as fluorine, steam if you took H2O and warmed it up, so now it's a gas, and so in the gas phase of H2O. In other words, if you ignore that there is an electrical or chemical interaction between them, that's what we mean by an ideal gas. Many gases, that is true, but not all the time. So we do need to be a little bit careful. But here's some good news. If we think about or ignore the interaction, and if it's justified because many gases have a small interaction, then what we think about here and what we work out could be applied for all these gases, and that's the best part. We could just take the atmosphere and go, okay, I have nitrogen. Well, actually, I only have 80% nitrogen. I think it's closer to 79% nitrogen, and something like 19% on oxygen, and the other 1.5 or 2% is a bunch of other stuff. But it doesn't matter what the other stuff is. It doesn't matter what percentage is nitrogen and what percentage is oxygen. They're all going to just be treated the same as a bunch of bouncing metal BBs through there. And so that's the discussion I want to have. So let's have a discussion about what we would get if we don't worry about what type it is and how they interact, which, like I said, is only justified if they don't interact much with each other, which for many times can be true, but not all the time. And so here's kind of the thinking. The thinking is, okay, let's talk about the pressure for a moment. And maybe it's best to kind of start off here and come back to this picture you've seen enough that, look, you can see the BBs bouncing around. You can see them hitting the styrofoam and holding it up. They're applying a particular pressure. And I would argue that that pressure coming from the impact of those BBs, right? That's our change in momentum, right? They hit, they bounce off. Remember, the change in momentum is related to the net force. Okay. And so if we go back to our mechanics and say, okay, here they're pushing off each other, which will give me a chance to show you a nice picture your author has. Might go pretty quickly here because it's near the end. Perfect, right there. Your author says, let's run through some mathematics. And in our short time, I'm going to let him do the mathematics, and so I'm going to encourage you to read his detailed mathematics. But I want you to understand where it comes from. And he says, look, and so here's his little box, and he says, imagine an atom in here. And so this is the atom. And so the atom is coming at the box, it's coming up, and so it has a horizontal velocity, v sub x, and a vertical velocity, v sub y. It hits and bounces off. And then, of course, it now has new components. And he makes some argument about what those should be. And like I said, I'm going to let you read that. But what I want to do is start off here conceptually by saying, wouldn't one of the factors, and I say one, because when I look at this, and I know this picture is only showing one atom colliding, the first thing that goes on in my mind is, how much energy do they have as they make impact with the wall? You know, what's their motion? Maybe you'd say, what's their speed? And I would think that that is a major cause of this. Now, you might say that when you have a whole box filled of them, some are going fast, some are going slow, so maybe we'll change this to their average kinetic energy. And I'll pause right there in case you're not familiar with the symbol, the bar over the top. We're going to borrow that from our math classes. Many classes will do that in their math. They said, okay, how do you want to label the average? And so we put a little bar over it. All right, so if I've got these things bouncing around and ricocheting around, some going fast, some going slow, I would say that pressure has to do with how fast they're moving. Now, I'm going to take that one step forward and say, wouldn't that be related to the temperature? Right? Isn't this what I'm trying to show here when I say, what does a cold gas look like? It looks like this. They're not moving very fast. They don't have much kinetic energy on average. What does a warm gas look like? And so we're going to then see that if we take our mechanics, we're going to say that the motion of them is related to their kinetic energy. And this, like I said, is where I kind of wish we had some more time, because your author does a good job here. He goes down here and says more about it. He goes through a couple steps of proof. He looks at a bunch of average speeds and trapped in a box, and attempting to kind of dive into his little proof. But I think our time will be better spent doing something else. So I'm going to say that it kind of makes sense, at least I hope to you, that the pressure is related to the motion of them. At least one factor is. And I'm kind of hoping you can also see, both in that conceptual picture and then later on when you study his math, that you would kind of expect the pressure to really depend upon, and I'll say how many atoms or molecules, but it's probably best to say the concentration of them. Because it's not just how much they have, it's really how many you have in a given volume, because those are the ones that are making the impact. So if you have a big container instead of this small container, you don't get more pressure just because you have more atoms in here. It's do you have a bigger concentration of them. So if this gets 3 times bigger, then I would expect the number of atoms to get 3 times bigger just to keep the same pressure. The fact that there's 3 times more atoms doesn't make more pressure. Now, if there is more concentration, in other words, if I go from here and I make a container that's 3 times bigger, yet there's 6 times more molecules in here, then I would say there's a higher concentration. And so you can see them bouncing around. In fact, you can even see this with the concentration. Look what you see when it is cold. When it is cold, I would say those molecules are moving slow, but they're in a small volume, and so they're really concentrated, and that's enough to hold up that styrofoam plastic piece. What if I make them go really fast? See, when they're going really fast, I would now say they're A, going really fast, but B, they're less concentrated. They've spread out. I mean, it's the same total number of BBs in there, but it's spread out over a bigger volume. So the concentration has gone down. And interesting enough, it still holds up the same piece of styrofoam. So it's applying the same amount of pressure. And so the pressure is determined by these 2 factors. So when it was cold, this was small, but this was big. Oh, when it got warm, then this was big and this was small. But the result still held up the same object. Still gave me the same pressure. Now, you might argue that those are the 2 factors, but I would say, even though that's true, there's probably some kind of multiplication constant that would depend on the units we use and, you know, how we're going to set this out. And so let's keep talking, because I call it a concentration, and I call that one factor because I think it's best to view it that way, the concentration. And so I like to say the pressure depends on 2 things. 1, the concentration, and 1, their motion. Okay. I already said their motion is going to be tied to their temperature here in a second. Their concentration, though, is really tied to 2 things. The number of atoms you have and the volume you have. So some people prefer to think as pressure caused by three factors. How fast they're moving, how many you have, and in what volume do you have them. And okay, if you want to do it that way, if that serves you better, fine. But I think this is easier to understand. You just got to remember concentration is actually two factors. So you might say there's three factors that determine the pressure. Or you just might say there's two factors, but concentration is two factors. So whichever way you find it a little bit easier, ultimately we're just going to have an equation, and take a look then at this equation. This is a very common equation. Many of you have probably already seen this. You probably have done something like this where you put a P for pressure, you put a T for temperature, the number of atoms, we'll use a capital N, and the volume we'll do capital V. And the constant, well, again, kind of depends on how you want to look at this, but the first one to do this is Boltzmann, so we like to call this Boltzmann's constant. So we like to say K sub B. Why don't I just give that number to you, 1.38 times 10 to the negative 23 joule over Kelvin. This gives me a chance to pause. Temperature. Doesn't temperature have three different scales we talked about? So would I use the Fahrenheit scale, the Celsius scale, or the Kelvin scale? And good, you guys are shaking your head on the Kelvin scale. How do I know it's the Kelvin scale? Well, as I mentioned earlier, pressure is determined by their motion, which is the only scale that corresponds a number with motion. That's the Kelvin one we just talked about. So if I tried to use Celsius here, it wouldn't work. Right? 0 Celsius would, I guess, come out mathematically to 0 pressure. It makes no sense. They're still moving. Only the Kelvin scale would make that work out. And of course, you can see that in these units of Boltzmann's constant. It's in the Kelvin scale. So know that I'm only going to use this formula if I'm on the Kelvin scale. Now, pressure is another one. Remember, we had absolute pressure and gauge pressure? And so what am I talking about here? What's pressure? Yeah, absolutely. This is the total pressure. This is not just the pressure above the atmosphere. This is the total impact from all of those BBs. And so if I'm doing a problem and they talk about the gauge pressure, I need to make sure before I start using this formula, I convert it into absolute pressure. So I take the gauge pressure and I add the atmosphere to it. And so that's my little warning here, is that this discussion here is what I would call total. Total motion, so it's got to be on the Kelvin scale, and total pressure, so it's got to be not the gauge pressure. And so just be careful as you're doing the problem, making sure you use the appropriate pressure and the appropriate temperature. Now, I'm going to keep going with this formula because it is better written in other ways, and so let me move volume to the other side. So I got PV equals, and we like to write the constants first, the number of molecules later, and then the temperature. Not that it's real important one way or the other, but this is kind of the standard way of writing it. And even here, I'm not going to quite put a box around it, but I will put a circle around it. Because what's really nice about this is it really shows these four parameters and how they're connected together. The pressure, the volume, the number of atoms, and the temperature. Of course, like I said, back here is kind of really nice. I guess it would be the same thing here because it really shows what causes the pressure. Well, the motion and the concentration. And then some multiplication factor for the units. But I want to pause here for just a second because I have a feeling most of you have seen not necessarily this equation, but you've seen PV equals nRT, where you use a little n. And maybe that one I'll put a box around, and I will say, these are really one and the same equation. For those of you who've done this before, could you tell me what little n means? Number of moles. Ooh. Wait. What's capital N? Number of atoms. So from a physics point of view, we really like it in this form. This form is actually telling us, like I said, the concentration. It's telling how many atoms do you have. There is a problem with that drives chemists crazy. How many atoms do you typically have in a container? Yeah, a lot. More than the number of stars in the known universe, by far. And so they like to group them together. Here's our grouping. Now, what do I mean by a group? Well, it's kind of like we do with a week. You know, we're in summer school. How long is summer school? 6 weeks. Now, you could have said 42 days, but you didn't. You said 6 weeks. Isn't it the one and the same? I mean, because isn't a week 7 days? And 7 times 6 is 42? And you chose then to give me an answer by grouping it together in a group. And that group is 7. 7 days make a week. Okay. So instead of saying 42 days, you decided to go with 6 weeks. I get that. I've got no problem with that. And that's what I'm trying to say here. This is a grouping. You could tell me this, it's 42 days, or you could tell me it's 6 weeks. You're just going to put them in a group. And in that case, it's a week. We often do that with cookies, you know. Hey, could you swing by the store and get me 3 dozen cookies? 3 dozen? Why don't I just get you 36 cookies? It's the same thing, right? But we like to group cookies in a dozen or donuts in a dozen. I don't know why exactly. We just like this grouping. There's something about saying 36 that, I don't know, sounds fatty. There's no way I'm going to get 36 cookies, but 3 dozen, well, that's fine. Right? It's just that we've grouped them together. Nobody walks into McDonald's and says, give me 100 French fries. It says, give me a bag of fries. We've grouped them together. We do the same thing with our atoms. It's just our group is really big. And so you might not be as familiar with it. It's like the group of a score. Do you know what a score is? It's not a very common one anymore.
12 dozen.
12 dozen. That's a gross. That's another uncommon one too. Yeah, so a gross is 144. Yeah. A score is 20. So when Abraham Lincoln gives his Gettysburg Address, 407 years ago, our founding fathers, what did he mean by 400? 80 years, right? 4 groups of 20. 4 score. And so it's just a grouping. And whether it's a common name to you or not, I hope you get the idea that we just group them. We group them in weeks, we group them in dozen, we group them in a score, we group them in years. Right? It's like, how old are you? Nobody says I'm 32,000 days. No, I'm 23, 24, 57, It's how many years? And you group all those together. Okay? So I'm going to do the same thing. I'm going to define an important group of atoms. And for some reason, this gives students a hard time. They have no problem with dealing with a week or a dozen, but they have a really hard time dealing with moles. And so this is my weird way of saying, don't make this harder than it needs to be. It's just a grouping of them. A mole is a group 6.02 times 10 to the 23rd. And so instead of 7 days, It is a lot more than 7. It is a big grouping. To give you some idea, I grabbed 6.02 times 10 to the 23 atoms of copper. Here they are. This is 1 mole of copper. And you can see that if I were to ask how many atoms here, they're a big number. And I prefer not to give it in big numbers. I'd rather give it in a sample. It's like, hey, how many are in here? I could say there's 1 mole. That's a lot easier than saying, oh, there is 6.02 times 10 to the 23rd atoms in here. We did the same thing with iron. It's almost the same size, actually. But aluminum atoms are a little bigger in spacing, and so the same number actually comes out to be a bigger volume. I'm not comparing and saying they're the same volume. I'm saying it's the same number of atoms. So here's 1 mole of aluminum atoms. Here's 1 mole of iron atoms. Here's 1 mole of copper atoms. This is the idea of by grouping them. We group them in a mole. Now, let's go back. How would you convert from one to another? I mean, if I told you summer school was 42 days and you said, okay, how many weeks is that? What would you do? Well, wouldn't you take the 42 days and divide it by your grouping of 7? You go 42 divided by 7. Right? You're asking how many 7s fit into 42? Because that's your grouping. That's what a quotient means. So I would say this. If you wanted to calculate how many moles do you have, and so there it is, little n. This is what this means. The little n is not quite the same as the big N. Right? This is the number. This is the 42 days, but this is the 6 weeks. This is how many groupings we have. So if I wanted to know how many groupings I have, I guess I would take the number of atoms I have and divide it by the number that fit in a mole. And so N sub A is going to be our symbol for our group. It's called Avogadro's number, because it was Avogadro's idea who said, we shouldn't talk about the number of atoms, we should talk about how many to group them. And so we put them in a big group. And so, again, you'll hear that as described as Avogadro's number, or for us in California, sometimes we like to call it the avocado number. All right, but it's Avogadro's number here, and that's how we would group it. So let me put a box around that, because if I put a box around this and then point over here, you could now see how these are really one and the same. It's just, how do you want to look at it? Do you want to look at it as the number of atoms, or do you want to look at it as the number of moles? In fact, I'll even run through the math here with you. And so this is saying that if I take this right here, so PV equals to Boltzmann's constant times the number of atoms. So like I said, in physics we like to look at the number of atoms. But if we'd like to replace that, you could say the number of atoms would be the same as the number of moles times Avogadro's number. Well, this is again like our summer school. This would be saying I've got 6 weeks, and each week is 7 days. So 42 days. And then times the t. Now, if you rearrange this and put the n first and the t later, then you have 2 constants multiplied together. And when you have 2 constants multiplied together, there's no point in thinking of it as 2 constants. You just might as well have 1 constant. And so what many of you are already familiar with is the r, the resulting number of multiplying Boltzmann's constant together with Avogadro's number. And so if I get out my calculator, I could calculate, and I have left my calculator in my office. So let me get my virtual calculator out. Okay, So if I take Boltzmann's constant, 1.38 times 10 to the negative 23, and I multiply it by Avocado's number here, 6.02 times 10 to the 23rd, I get a very important number. That is 8.31. 8.31, and what are my units? Well, I guess Boltzmann's constant was joule over Kelvin. And I guess I didn't put any units here, but I suppose I should have. This would be 6.02 times 10 to the 23 atoms per mole. And so this should be then per mole. And I must admit, joule is not very inviting the way it is written, because our little equation has things like pressure and volume. But remember, if pressure is in pascals, which is a Newton per square meter, and you multiply it by a volume that's in cubic meters, this is going to come out to be Newton times meter, which is a joule. So I'm going to do this. I'm going to take a joule and separate it into a Pascal times a cubic meter. This is my way of saying that if I'm going to go ahead and use this equation right here, and I'm going to measure in moles, R has units with it, and I have to match it over here. And so if I use the units of pascals and cubic meters, then I would use 8.31. However, I got to admit that I bet most of you, if you've seen this equation before, were coming from a chemistry class and you didn't measure your pressure in pascals, you measured it in atmospheres. And we said that 1 atmosphere was 1.031 times 10 to the 5 pascals. Also, I bet a lot of you measured not in cubic meters for your volume, but in liters. That's why this time I decided to bring out the definition of a liter. I mentioned this before. This is a liter. The definition of a liter is something that is 10 centimeters by 10 centimeters by 10 centimeters. 1 liter. Whereas a cubic meter is about the size of this desk. And so if I were to ask you how many liters are in a cubic meter, I guess I would go 10 this way, 10 this way, 10 this way. So this box, there would be 1,000 of these boxes in here, right? It would be 10 by 10 by 10. And so there must be 1,000 liters in 1 cubic. So this would change the units to atmospheres times liter, Kelvin per mole, and it would change the number to, let me just check my math, to a number that you might feel more comfortable with. Let's see, 8.31 divided by 1.013 times 10 to the 5 times 1,000. Yeah, 0.0821. And so I have a feeling that you guys coming from chemistry are thinking R should be this number. And I just want to emphasize, if you use these units, that is R. And so we probably won't use much of R this way, because we'll probably want to talk about the units in energy, which is in joules. And pascals and cubic meter works much better than atmospheres and liters. And so that's my little warning for you. This was a long way then of saying that if we kind of think about the pattern here for our third and final piece of this chapter, is that we can use either one of these two equations. Either PV equals to Boltzmann's constant times the number of atoms times T, or PV equals to nRT. Those are really saying the same thing. That's what I'm trying to emphasize. And the R could be 8.31, or it could be 0.0821. It really depends on if you're measuring your pressure in atmosphere and volume in cubic meters, or if you're measuring your pressure in atmospheres and your volume in liter. The choice is yours. But I feel like I need to give you guys a little heads up, because many of you come from chemistry before you came here, and you've done a lot of this. And so you're going to look at me crazily when I start using this number. And so I wanted to make sure I explain it. It's the same thing, it's just a unit conversion. You might even look even more weird at me when I start using the total number of atoms instead of the number of moles. And we're really talking about the same thing. In fact, this gives me a way, as we get here towards the end, to say, you know what? I find it kind of convenient to avoid the units for R altogether. I like to do this. Let's rearrange this equation so it says PV equals to NT equals to R. You see, let's pretend that I have a particular gas. Now I have 3 of them here that I can show you. But this one here has a little container of molecules, and it's the same one you guys saw in the lab. It's got a little valve, it's got a pressure gauge up here. Now I got to be a little careful with this pressure gauge. Remember, reads in gauge pressure, so I've got to add 1 atmosphere to it. But I would say right now I have some initial condition. I have a volume, a number of molecules, I have a temperature, and I have a pressure. So let me come over here and just write initial pressure, initial volume, initial number of molecules, and initial number of initial temperature. Because if I come over here and then take this and put it then in the hot water, you will hopefully see the pressure gauge go up. Now, because I'm in a metal container, I would say the volume barely changed. I know there's a little thermal expansion, but ignoring that, I would say the volume stayed the same. I guess I would also say, because the valve's closed, the number of molecules stayed the same. And so what ended up happening is the temperature went up, and then so did the pressure. And I could just equally put it on the cold ice and have the pressure go back down. And so I have what I like to describe is then a final pressure a final volume, a final number of molecules, and a final temperature. And so if I just ignore the R altogether, I don't have to even worry about the R. I can just say my initial is equal to the final. And then we can change it as needed. You might have noticed in that experiment I just did, I would say this, and so I'm going to put if. If the volume is held constant, and if the number of molecules is held constant, because that's what I just did, this would then say, I guess the volumes would cancel off and the number of molecules would cancel off. I would have initial pressure over initial temperature must equal final pressure over final temperature. And that's what I just did. What I did was warm up, and so the final temperature went up. I went from some initial to some final. This went up. And then according to the math, the pressure should go up by the same proportion. And of course, I didn't measure anything more accurate. That's what the lab was for, but I think you saw that. On the other hand, what if I did this? What if the temperature is held constant and the number of molecules is also held constant? What would that say? Well, I guess these in the denominator would be the same as these in the denominator, so initial pressure times initial volume would be the same as final pressure over final volume, or times final volume. And this is kind of an easy experiment to show too. In fact, you might even recognize it as Boyle's law, because the first one to discover this was Boyle, and so we call it Boyle's law. But I want to emphasize that I'm just going to refer to it as the ideal gas law. Oh, by the way, the first one, pressure and temperature. That's somebody else's name, not quite as popular. Remember from the chemistry? Is that Charles' law? There's a Guy Lucy and a Charles and a Boyle's. I forget which one is which, but, well, the Boyle's one I know, just because it says on here all the time I read it, Boyle's law. All right. So Boyle's law is kind of the easy one to remember for me. But what I've done here is I've just kind of have this pressure gauge that so you can read it, and I have a syringe right here, and I don't know if you can see the edge of the syringe. It's right here. It looks like 25. And I'll just leave it at 25 cc's. But if I clip it together, I have a volume of 25 cc's and a pressure of 15 psi. Now, forgive the units for a moment, but watch what happens, again, according to this math, that if I were to, say, cut the volume in half, then the pressure would have to double. And so, sure enough, I'll take my syringe and go from 25 to about 12 and a half, right about there. And then the pressure is 30, well, close to 30. So it didn't quite meet the math, but pretty darn close. And since we're low on time, I won't go too much other than just to pull it back and forth and show you that as the volume gets smaller, the pressure gets higher, again, because of that relationship. Well, let me show you the third combination we could have here. What if we had pressure equaling a constant and the number of molecules also equaling a constant? I guess then I would get volume over temperature and volume over temperature. And this would say then as you change temperature, you change volume. And again, what I want to emphasize is let's not try to remember each one individually. Like I said, I'm not even going to try to remember whose name goes with which one. I'm just going to say if you put all these three laws together that were discovered separately, Boyle's and Charles or Guy Lucy's, or maybe the other way around, this is what it's trying to say. And so we call this the ideal gas law. Now, to the best of my ability, I'll try to show this to you. But here I have a little container that works kind of nice. It actually allows me to kind of maybe lift it up and lock it into place. And so I would say the volume is the air that's in here and in this cylinder. And so the volume's kind of spread out because I can put it in this hot one, but I can't put all of it in the hot one. But it's nice to kind of watch this because if I put it in the hot water, it goes up. The pressure is actually determined by the weight of this thing. And so by allowing that thing to move, I can keep a constant pressure. And so now as it cools down, you'll see it decrease in its volume. So if I put it in the ice and say the temperature goes down, the volume's going to go down. If I put it in the hot water, well, then the temperature's going to go up and the pressure is going to go up. And so again, probably the best thing I could say for you is to remember that connection and then look at the problem and say, okay, what kind of experiment do I have? Do I have these things that are a constant or not? Well, one last thing, and we'll get out of here for the next class, and I'll just kind of have to give you the formula in here, but your author, and it's right here on the screen, in this mathematical derivation, he does correlate the speed, what's called the RMS speed, with the temperature. And so he says this, that 1/2 times m times the average speed squared is equal to 2/3 times Boltzmann's constant times the temperature. I'll take one step of mathematics here and say that if you move the m to the other side and then take its square root, you're going to get the speed. And so now we have a mathematical way of answering. And so like I said, I didn't have time to go through the proof here after the test. But if you go through his proof, you'll see here, and then of course he's got the little formula right here that says, okay, what is the average speed of all these guys? So they're bouncing around. And if I were to tell you the temperature is 300 Kelvin, oh, did you catch that? Did you notice? Has to be on the Kelvin scale, right? Because Kelvin scale is the only temperature scale that is connected to the motion. But if I put in here 300 Kelvin, I then can tell you the speed. And that's the end of the chapter and the last of it. All right, so I'll call it quits. I'll give the other class a chance to come in here. We'll go over to the lab and do our next experiments, and we will go to chapter 14 tomorrow. All right. See you guys over.